Okay, we just finished up talking about strain. We talked about what happens when we stretch a spring and some of the reactions. So now what we're going to talk about is general materials and what they look like when they're under load. Okay, so just to recap, when we had a spring, what it looked like was we had a graph that we created of force times the change in length, and what our spring looked like was some sort of straight line. Okay. When we talk about materials, we don't use force and change of length. Well, recall that we had a couple of terms that we've used previously. We had stress, say if it's a normal stress, which is a force per area. We also have strain, which is a change of length compared to length. So if we kind of compare these things, we have a similar force, and we have similar here where we have our change of length and a change of length. Okay, so it makes sense that we should have a graph that is generally organized with the force term and the change of length term on the bottom. Okay, and so this would be what we would consider to be a stress strain diagram. And for a general material, what's going to happen is our stress strain diagram is going to look like this, okay, for a while. So if we're in a point where our material is a spring-like, okay, so we stretch it, and then when we release that tension, it goes back to its normal point. Okay, so when it's in this spring zone, it can flex back and forth, and will eventually get to its original point. However, if we stretch it too much, we could think about what might happen. So as we stretch and stretch and stretch and stretch and stretch, something happens within the material and it no longer is able to return back to its original point. We've deformed it. So on my stress and strain diagram, what happens in that point is when it deforms, we get to a point where it starts to stretch more, meaning we get more and more strain. And we have usually small changes to our force. Okay? So we have two different distinct zones. We have this portion here where when we stretch it, it can return back to its normal spot, and it works in a predictable manner. Okay, and this is what we call the elastic zone. Okay, it behaves like an elastic. All right, so that material can stretch and then go back to its original point. Stretch, return back to its original point. We then have a case where if we exceed the limits, then we are into what's known as the plastic zone. Okay, so the plastic zone is one where we have permanent deformation that occurs. So if we stretch it to that point, then we're going to see that deformation when we unload. So it'll never return back to its original shape. At the transition point, what we have is a couple things. Okay, so first of all, if we quantify how much stress occurred when we transitioned from the elastic to the plastic zone, that happened at what we consider to be the yield stress. so I put a Y there, but that's our yield stress. Okay. In and around that zone as well is where we have our proportional limit. Okay, so our proportion and proportional means that there's a ratio that's attached, and that's this zone where we have our proportional zone. Okay, but at some point here we no longer are proportional, and at that point we don't have a linear relationship. Sometimes we might indicate that as a capital P as our proportional limit. Okay. Somewhere as we keep stretching and stretching, we're going to get to some endpoint where this thing might break. Okay. And at the point of failure, we have another stress that we talk about, which is stress U, my ultimate stress. And sometimes we might call that my ultimate strength as well. So just like when we had a spring, we had some cases where when we had a spring, we discussed that if that spring was weaker, okay, or I had a spring that was stronger, we would have materials that, or we would have a reaction on that diagram that would be different. Okay? And we could quantify some things, so what my force and what my change of length was, by looking at what was the slope of that line. Okay, so not just for springs where we had a slope, but we also have a slope for this line here, which is important to us. So my slope is equal to, I had K before when I dealt with a spring. This time I have a capital E. And what the E is sometimes we might call it the modulus of elasticity. Okay, or else sometimes we also call it Young's modulus. Okay, so that E value tells us how stiff that spring is, or how stiff the material is. So if we expect it to be able to stretch a lot, then it would have generally a lower slope. If it was going to stretch a small amount for a given load, then it would have a higher value. Okay, so the E value is a measure of how stiff the material is. Okay, so this is a measure of the stiffness. Okay, in the elastic zone. And we can also create an equation for that, where E, just like when we calculated our spring constant, we saw that K was the slope, rise over run. In this case, E is our rise over run, which is equal to rise being my stress compared to my strain. Okay, so Young's modulus is going to be E, which is a measure of stress per strain, or in symbol form, we have stress divided by strain. Units of E is pascals. Okay, so a little different than our K value for our spring, but tells us a measure of how stiff the material is and how it is expected to deform under load. If we go to the tools that you have, which is in your academic supplement, you have a section on stress, strain, and modulus of elasticity. Okay, so just wanted to point out a few things. So we did have our direct stress, which was our force per area. And again, reminder that in the textbook they've used P as their force, okay, through this section. We did have our strain, so our strain was our change of length per length. And we had our modulus of elasticity, okay, and so what it was a measure of stress per strain. They've gone one step further, which is a good idea, and to say that when we have E is a measure of, stress over strain, which is equal to, well, stress is equal to a force per area. So they've gone P over A divided by strain, which is a change of length per length, okay, which gets us to this equation here. Or else simplified, so the over A on the top, the A goes to the bottom, the over L on the bottom goes to the top, and what we're left with is a really powerful version of this Young's modulus equation, which says E is equal to the force times the original length of an object divided by the area and divided by the change of length. Okay, so it may not be that obvious in your supplement that you've got kind of this connection between these versions of the equation, but E is equal to PL over A times the change of length is a very useful equation for a lot of your calculations. Okay, we can use that equation to find out, given some material properties, E, forces, and geometry, we can find what is the expected change of length. And that's a very typical question for you at your third class level. Okay, so let's look at a question out of our worksheet. Calculations in the elastic zone. Okay, so we have a steel beam. Okay, and I don't know exactly what that beam looks like, but it has a cross-sectional area of 4.2 centimeters squared. The whole thing is 6 meters long. And I'm going to apply a tension of 60,000 newtons. And I'm curious about how much will it stretch. I've given you the E value for steel, so 200 gigapascals. Okay, so let's recall that materials, solids, are very strong, and we're dealing with large numbers. E of steel, typically 200 gigapascals, so we have a fairly large number already that we have to deal with. Okay, so if we want to know how much it will stretch, we're going to use our equation. So E is equal to PL over A times the change of length. And rearranging this equation, I would get my change of length is going to be equal to PL over AE. Okay, let's look at units for a second. So base unit of P is a Newton. base unit of L is going to be a meter. My area is going to be meters squared. And my E value is a Pascal, or a Newton per meter squared. Okay. In the end, all of this is going to be giving me a change of length value in meters. Okay, so before I get started and diving into these equations, what I want to do is make sure that I have everything in the correct units. So if I go to check, I have a length of 6 meters, that's good. I have a pull of 60,000 newtons, that's good. I have an area of 4.2 centimeters squared, and I'm not very happy about that unit. Okay, so let's do a conversion. Be very careful with this conversion. It is a hard one. Okay, looks simple, but very often mistakes are made. So what we have is 4.2 centimeters squared, which really is a centimeter by a centimeter. Since I have centimeters twice, what it means is that I'm going to have to convert twice. So times 1 meter per 100 centimeters times 1 meter per 100 centimeters. Don't see the square and forget to convert twice. Very common mistake in these questions. So 4.2 divided by 100 divided by 100 gives me 4.2 times 10 to the negative 4 meters squared. Okay. I have one last value, which is my E of steel, which is 200 GPa. And what I want is that in pascals. So a G is worth 200. The G is worth times 10 to the 9 pascals. All right. So back to our calculator talk. You got to make sure you're good about using your calculator. All right. So don't forget to use the EXP button. It's going to be very helpful for you, especially when you have exponents and large numbers, top and bottom of a fraction. So let's enter this in, and please work along with me and make sure that you can punch this into your calculator and get the correct answer. So the force P is 60,000 newtons. The length 6 meters. We're going to divide that by the area, 4.2 times 10 to the negative 4 meters squared times 200 times 10 to the 9th pascals. So 60,000 times 6 divided by 4.2 exponent negative 4 times 200 divided by 200 EXP9. See, I almost made a mistake myself. 4.29 times 10 to the negative 3 meters. Okay. Before I just say that it's good and move on, what I want to do is make an estimate as to, is this even reasonable? Okay. I've taught this for a long time, and I've seen lots of answers come out of questions like this, where a student will say that 6 meter long beam, when I put it under load, stretched by 42 meters. And it's not reasonable. It's not reasonable. So if we think about it, how much we have this 6 meter long beam, you know, it's the width of your house, and we put some load on it, how much is it going to stretch? You know, maybe a millimeter if we put it under a heavy load. It's not going to stretch much. So let's make sure that when we get an answer, it's within reason. So here's my answer. you know, it's about 0.4 millimeters. I think I'm in the ballpark. And if you're not in the ballpark, the most likely thing that you've done is made a mistake, either by getting the wrong units, converting your area wrong, or calculating your area wrong, or doing your calculations here. Okay, so make sure that the answer you get sounds reasonable, and if it doesn't sound reasonable, then you've got a few spots to hunt around for solutions. Okay, just before we get to our final example in this section, we have one more thing to talk about, which is factor of safety. So a factor of safety, when we have an object, we would like it to stay usually in the elastic zone. And the reason why we have it in the elastic zone is that it's predictable. So we know we have that straight line curve where we can move up and down, and if we relieve the pressure on the object, it goes back to where we started. Okay, that's great because we have predictability. However, that doesn't mean that it's going to be 100% safe. So we add factor of safety to something to make sure that not only is it going to be operating in a predictable zone, okay, but also when it's inside of any loading, we know that we're well away from the point of failure. So if we talk about our factor of safety, if we have some object and, you know, it's going to load like this and it might break here, really what we're doing is we're comparing the ultimate stress, the breaking point of the material, compared to whatever state of load it's under. And if I considered what my factor of safety for the little drawing that I created, I don't know, maybe I'm like 1, 2, 3. So maybe my material is 3 times stronger than the load that I have it under. And that's how I calculate factor of safety. So factor of safety is going to be a measure of what is the ultimate breaking strength of the material compared to the stress that I'm under. And sometimes we call that the actual stress, so if it's under a state of load. Or else sometimes we say if we're in a design or we're trying to create some device that has to withstand some load, we might consider it to be what is the allowable design stress for the material. Okay, so we have a factor of safety comes into play. Okay, so let's finish off our question. Okay, so we have a bar and it has some cross-sectional area and it's being stretched once again. So same sort of questions as we had previously. So I'll just draw a little diagram. I got my beam. Okay, it's 5 meters long and it has a cross-sectional area, so that guy, of 20 centimeters squared. I have it under a load of 150 kilonewtons, and the E for the material was 200 GPa. And the material has an ultimate strength of 600 MPa. Okay, and I have a whole series of questions about this case. Okay, so first thing that I want to do before even diving into all these questions is get everything I know into the units that I want. Okay, which means that I'm going to have a pull of 150 kilonewtons, but I want that expressed in newtons, so 150,000 newtons. We have a area of 20 centimeters squared, but I want to convert that to meters squared. So don't forget we have to divide by 100 twice. So 20 divided by 100 divided by 100 gives me 2 times 10 to the negative 3 square meters. E is in gigapascals, but I would prefer to have it in pascals. So I'll replace the giga with a 10 to the 9. My ultimate stress, 600 MPa, M worth times 10 to the 6th pascals. Good news is my length is in the right units, 5 meters. Okay, so we want to find the stress in the bar. Okay, so this is being pulled axially, okay, or in the normal direction. So the stress they would refer to would be a normal stress. So stress is going to be the force spread out over the area is going to be 150,000 newtons divided by my area in square meters, so 2 times 10 to the negative 3 meters squared. And what I get is 775 million. Units are newtons per meter squared, or that would be a pascal. And sometimes when I'm talking about stress, I might want to simplify that to say 75, and I've got 6 zeros, which is equivalent to a mega pascal. Okay. So part B wants to know the strain produced. Okay. Well, I know that E is equal to stress divided by strain, which means that my strain is going to be equal to my stress divided by Young's modulus. So I have my stress, so 75 pascals compared to 200 times 10 to the 9th pascals. And I get a strain of 3.75 times 10 to the negative 4. So again, when I use strain, I want to just be careful that I'm left with no units. So it is the case here, pascals and pascals have canceled themselves out. Okay. Part C, the amount the bar is stretched. So strain is going to be equal to my change of length compared to the original length. Or if I rearrange, my change of length is going to be equal to E times L. My strain times L. So 3.75 times 10 to the negative 4 times my length, 5 meters. 1.875 times 10 to the negative 3 meters. Okay, so my object, again, that was 5 meters long, it was under some load, and it stretched just under 2 millimeters, and that's probably a reasonable amount of stretch for a steel object. Okay. Last thing is the factor of safety. Factor of safety is how much can it hold? 600 times 10 to the 6th pascals compared to how much load is it under. So we had our 75 million pascals. And my factor of safety is 8. So what that means is that the object, even under that amount of load, still is 8 times away from it being at its breaking point. Okay, that's the end of this section on stress and strain, dealing with diagrams, calculations, calculations within that elastic zone. One thing just to note before we wrap up, when we do these calculations, so we have these elastic zone calculations, they're only valid within the elastic zone. Okay, so they're no longer valid once we've passed that yield point or the proportional limit.